Welcome back to my lectures on groups, rings, and fields. Our next topic is direct products and finitely generated Abelian groups. We have used the direct products in our earlier examples even without knowing or defining what a direct product is. So let us start with defining the direct products from existing groups. It's a derived group, meaning it is constructed from existing groups. So when you want to define a group, what we need is essentially the elements and a binary operation which satisfies all the group axioms. So let us start the definition of this. Let G1 comma G2 dash dash Gn be groups. Then the direct product of these n groups is defined as but the notation is exactly G1 cross G2 cross dash dash cross Gn and a star where an element of this group is A1 comma dash dash An, where Ai belongs to Gi, and the star, the binary operation is defined as A1 dash dash An star B1 dash dash Bn is equal to A1 B1 comma dash dash comma An Bn for all Ai Bi belongs to 0. So this is a definition of the direct product, the group direct product. Now we need to establish that this is really a group, meaning we need to prove that all the group axioms are valid. So the G1 dash dash Gn star is a group because star is closed. That is obvious from the definition, meaning if you take any element from two elements from here, this is a valid definition. And we need to identify the identity of the group. E1 dash dash En is the identity of G1 Gn, and the inverse of any element is A1 inverse An inverse. This also belongs to G1 Gn. and is associative. Actually, because each of GIs are groups. So this is really a group, this with this binary operation. Now let us establish some results on direct products. The first one we are going to try is this. Zn is cyclic if and only if GCD of Mn is equal to 1. And if one of this is true, then Zn is isomorphic to Zmn. The way we are going to prove is this. It's like this. There are two parts here, if and only if condition. So what we are going to do is let GCD of Mn is equal to 1. Then that should imply Zn is cyclic. That is one part. The second part is GCD of Mn is not equal to 1 implies Zn is not cyclic. And once it is done, then we are going to create an isomorphism here to show that these two are isomorphic. See, GCD of Mn is equal to 1 means there is no common factor between M and N. They are prime to each other. Zm and Cn, Zm and Zn are cyclic. And let A, B be generators of Zm and Cn respectively. Now our claim is A, B generates Zm and Cn. If you can prove that, then Zm and M cross Zn is cyclic. How do you prove this element generates this group? We need to find out every element of this group can be expressed as a power of A, B. So A and B are generators implies A to the power of M is equal to 0 and B to the power of M is equal to 0. So A to the power of so every multiples of M, for every multiples of M, A to the power of that multiple will be 0. Similarly, every multiples of N, B to the power of that multiple will be 0. So A to the power of P is equal to 0 when M divides P, and B to the power of P is equal to 0 when N divides P. We need to find out a P here such that is equal to the identity, and see that if that number is equal to Mn, we know that this element can generate all the elements of this group. So this implies a comma b to the power of p is equal to 0 comma 0 when p is a multiple of both m and n. And this, then the lowest value of such p is mn because GCD of mn is equal to 1. And that implies a comma b can generate all elements of z comma zn. Implies zm zn is cyclic. Here let GCD of mn is equal to d greater than 1. This implies d divides m and d divides n. This implies a comma b, I'm assuming that a and b are generators here. We have to take generators here because otherwise it is not going to even populate or create all the elements of Zm or Zn. So it has to be generators. So assuming that a comma b are generators of Zm and Zn, this is equal to the power of p is equal to 0 comma 0 when p is equal to mn by d, which is strictly less than mn because d is greater than 1. And that implies a comma b cannot generate all the elements of Zm Zn, implies Zm Zn is not cyclic. Now we need to establish that isomorphism. So I'm going to just define the isomorphism here. You can verify it. So isomorphism Zm cross Zn to Zmn defined by phi of 1 comma 1 is equal to 1. So this is a generator of this and this is a generator of this. When this is a generator of this, that means phi is well defined. When this is a generator of this, that means this is a onto and bijective mapping. So here phi is a bijective homomorphism or is a isomorphism, and that implies Zm Zn is isomorphic to Z. Now let us generalize this result to n cyclic groups. So Zm1 cross Zm2 cross Zmn is cyclic if and only if mi comma mj or GCD of mi comma mj is equal to 1 for all 1 less than I comma j n and I different from j. And in that case Zm1 cross that Zmn is isomorphic to Z of M1, M2, Mn. This is just a generalization of the earlier result. We are going to use this result to prove another simple result. We'll prove another result. Let n belongs to Z, any integer, any positive integer. Then Z to the Zn is isomorphic to Z PR P1R1 Z P2R2 Z P M R M, where PI's are distinct primes and actually distinct prime factors of n, and R1 dash Rm are integers. This is a very simple result when we use the previous result. See, every n, every integer n can be written as P1 R1 P M R M for some primes Pi's and Ri greater than 0. This is possible. If you take any integer, you can factorize this. And that implies Zn is equal to Z of P1 R1 Z of P2 R2. This will be, we'll write one more step here. Then P2 R2 P M R M, and this is isomorphic to C P1 R1 C P2 R2 Z P M R, and that's what we want to prove. Our next result is on the order of an element in a direct product. So the result is this. The order of A1 dash dash AN in G1 GN is the LCM of R1 dash dash Rn, where Ri is the order of AI in Gi. By the way, there is another notation for this direct product. It's pi I is equal to 1 to n Gi. So the order of A1 comma dash an in pi I is equal to 1 to n gi is the lowest integer p such that a1 comma dash dash an to the power of p is equal to e1 dash dash en, where ei is the identity of gi. For each I, ai to the power of ri is equal to ei, and ai to the power of any multiple ki ri is also ei. So the order of a1 dash dash an in pi I is equal to 1 to n gi is the lowest multiple of each of ri's, and that is equal to the LCM of r1 dash dash r. We'll do an example here. Let us find the order of, say, 3, 10, 9 in C4, C12, C15. This is an element in this direct product, and we want to find out the order of this. So the order of 3, 10, 9 in C4, C12, C15 is the order of, the LCM of is equal to the LCM of order of 3 in C4, order of 10 in C12, order of 9 in C15. And that is equal to, this is actually 4 because 3 is a generator of C4. So this, the 10 will, the 10 to the power of 6 will become 0 in C12. So the order of 10 is 6 and order of 9 is 5 in C15, and that is equal to 6. Now let us take a look at the groups that are finitely generated. There are different kinds of, two types of groups that you can find that are finitely generated. Let us see the difference between those two kinds of finitely generated groups. So the definition of a finitely generated group goes like this. A group G is finitely generated if there exists finite number of elements, say x1 dash dash xn in G, such that every element in G can be expressed as a linear combination, this is not the right word, combination of xi's. When I say linear combination, what I meant is if G belongs to G, then G is equal to n1 x1 plus dash dash n r xr for some integers ni's. This is not really a linear combination, but I'm going to borrow this definition from linear algebra. By n1 x1 I meant ni xi, that means xi's are added or binary operated ni times. This is not a multiplication of ni with xi. You can also write it as xi to the power of ni if the binary operation is a multiplication, or binary operation is denoted by a multiplication sign. So this is what I meant by linear combination. Okay? So this is the definition of a finitely generated group. Now let us consider two different types of finitely generated groups. One is Z cross Z, and another one is C2 and C3. Both of them are finitely generated. This one is generated by one zero zero one, and this is also generated by 1 0 0 1. There are more generators, but one of the generators are like this. Now, if you take any element from Z cross Z, let us say take 4, 7, that can be written as 4 times 1 0 1 1 0 plus 7 times 0 1. And there is, once these elements, the generating elements are fixed, there is only one way of writing any element in Z cross Z. They are uniquely expressed as a linear combination of the generating elements. Whereas here, if you take, let us say, 1, 2, it's an element of this. So you can write it as 1 times 1, 0 plus 2 times 0, 1. But this is not the only way of writing this. You can also write it as 3, 1, 0 plus 2, 0, because this is actually 3, 0 plus 0, 2, and 0, 3 in Z2 is 1, so it's 1, 0 plus 0, 2, 1, 2. So this element is not uniquely expressed in terms of generating elements. So there is a difference between these two. So when a group is finitely generated and it is uniquely expressed as a linear combination of the generating elements, then it is called free groups or torsion-free groups. So finitely generated free groups or finitely generated torsion-free groups. These are not torsion-free. These are torsion-free. So there is a difference between a finitely generated, there are different types of finitely generated groups. Now let us see the formal definition of a torsion-free group. So a finitely generated group G is torsion-free if every element of G can be uniquely expressed as a linear combination of generating elements. Example, Z cross Z is torsion-free Z2 cross C3 is not. And if you take Z3 times Z is also not a torsion-free group. Now, normally we'll take a, okay, so let S be the set of all generating elements of a torsion-free group G. So sometimes we'll write it as G of S, the group generated by the set of this element. This we use it only when it is torsion-free. So the set of generating elements of a torsion-free group is called a basis. A basis of the group. Now let us see the structure of a torsion-free group, a finitely generated torsion-free group. Meaning we are trying to find out, going to find out a group that we are familiar with, which can be isomorphic to a torsion-free group. So the result is this. Any torsion-free group is isomorphic to Z times Z R times for some integer So, the way we are going to prove this one is, let S be a generating set of a torsion-free finitely generated torsion-free group G. So that implies every element G in G can be expressed as G is equal to n1 x1 plus dash nr xr for some integers ni and xi belongs to S. That is a definition of torsion-free, finitely generated torsion-free group. So now define a map phi from G to Z cross dash Z R times. By phi of n1 x1 plus dash nr xr is equal to the n tuple n1 dash nr. We are assuming that S contains R elements. Okay? Let us assume it's a finitely generated, so it's a finite set. S is a finite set, so I'm going to assume that the cardinality of S is equal to R. So this is a bijective homomorphism. Phi is a bijective homomorphism. And that implies G is isomorphic to Z R times. And because of this map, we can say that every base, the number of elements in every basis of a torsion-free group is a constant, because this is isomorphic to Z cross R times. Okay, so if you take another basis, that also have to be isomorphic to this. If you take another basis, that also have to be isomorphic to this. So every basis of G should contain R elements. In other words, the number of base elements of a finitely generated torsion-free group is a constant. So what we have found is the number of elements in any basis of a finitely generated torsion-free group is a constant. That constant is called the rank of the group. The similar term in linear algebra, the rank is dimension. But this is different because we are not dealing with the fields here. Example, the rank of Z cross Z is